Hello everyone, welcome to the ninth tutorial for EC457A. So I had a week of delay for this tutorial, and the reason was that the first time that I recorded this tutorial, I realized that my voice was not recorded uh, in the video clip, and actually it took me a while to find some time and re-record this tutorial. So what I'm gonna do now is to walk you through the stuff. I'm not gonna write anything because I have written them like before for the first record of this video, and I'm just gonna walk you through and explain the steps and in the examples. So let's get started. So the first example that we are going to discuss is the dynamic games with an example of entry deterrence. We have two players, two firms, and the order of play is that the entrant decides whether to enter or stay out. So entrant is the first player, and the second player, incumbent, if the entrant enters, the incumbent can collude or fight by cutting the price drastically. Okay, so this is a table for this game. Entrant can either enter or stay out, and the incumbent can collude or fight. Okay, so the payoffs are the market profits, which is which are 300 at the monopoly price and 0 at the fighting price. This is the tree that we can create for this example. So the entrant can either enter or stay out. So if the entrant stays out, this will be the payoff. 0 for entrant and 300 for the incumbent. And the reason is that when the entrant stays out, well, incumbent has no reason to collude or fight. But when the entrant enters, the incumbent can either collude or fight. So if it colludes, the payoff for entrant will be 40, and the payoff for entrant for incumbent will be 50. So that will be the incumbent's best response to this action, to that entering action of the incumbent. And entrant. And so incumbent can fight, in which case the incumbent gains no payoff, and the entrant loses 10. So this is the tree that we can actually create for this deterrence game. And also the Nash equilibrium for this game is stay out for the entrant and fight for the incumbent. Why is this the case? The reason is that if we are to find a Nash equilibrium for this problem, let's see. Let's start from this cell. We can move to the left side because 40 is greater than -10, and we can also move downward because 300 is greater than 50. Also, here we can move to the right or to the left because both cells have the same amount of payoff. Also, from this cell, we can move downward because 300 is greater than 0. But when the entrant stays out, there's no reason for the incumbent to collude. But the incumbent can fight to increase its profit. So this can be a reasonable answer in considering the Nash equilibrium is stay out and fight. Uh, okay, I think this is for this example, dynamic games. Let's move on to the other one, infinitely repeated games. So this is a 3 by 3 matrix, 2 players and 3 actions, A, B, C. So for each player, we have 3 actions, A, B, C, and we are going to consider like 3 strategies. The first strategy is Grim, which is also considered known as trigger, and the second example is tit for tat. And we have another example, that's another strategy. Another strategy that says play C in odd moves and A in even moves. Okay, so note that we sometimes call the actions as strategies, and we also have some strategies here. So we are using the word strategy interchangeably for like actions or action or strategy. We can choose any of these 3 strategies like Grim, Tit for Tat, or strategy number 3. We can choose either of them for like any of them for each player. And also note that in this game, at every time slot, the players act simultaneously. Okay, so we want to compare these 3 strategies like against one another. So, for example, let's say that player 1 plays the first strategy, which is Grim or Trigger. So it says that start with C, action C, continue to choose C unless other player chooses B or A, then choose B or A. And let's consider that player number 2 plays the second strategy, tit for tat. So it says that start with C, then repeatedly play the last strategy played by the opponent. Okay, so in this case, they both chose their actions simultaneously. So P1 chooses C because it's playing Grim, and P2 chooses C as well. Now, for the next action of P1, it says that continue to choose C unless other player chooses B or A, then choose P or A. So in this case, we can see that the previous move or action of player 2 was C, so not A or B. Therefore, player 1 continues playing C. And for player 2, we also it says that repeatedly play the last strategy played by the opponent. So the last strategy played by the opponent is player 1 here. It was C. So player 2 plays C. And this goes on and we can find the summation of these actions for both of them it will be like equal because both are playing this cell and they get 10 in each time slot in each step that they move forward. So it doesn't matter if player 1 plays strategy number 2 and player 2 plays strategy number 1. The result will be the same. So in this game, we can say that tit for tat has no advantage over Grim, or Grim has no advantage over tit for tat. So if one player plays tit for tat and the other plays Grim, they achieve the same result. Now for here another game. Let's say that player 1 plays Grim and player 2 plays strategy number 3. Says that play C in odd moves and A in even moves. So for player 1 it's Grim, so player 1 chooses action C. For player 2 it's strategy number 3, so it says that play C in odd moves. So this is the first move, number 1, so it's odd, so it plays C. And for the next time slot, for the next step, or for the next move, Player one is playing Grim, so it says that play C unless the opponent plays A or B or played A or B in its previous move, then play A or B. So we can see the opponent played C, so player one plays C here. And for player two, because it's playing this strategy, it says that play A in even moves. So this is move number two, or the second move. So player number two will play A. So we can see that for player number two, it doesn't matter what action the opponent chooses. So player two will always play CA, CA, CA. But for player one's moves or actions are dependent on the player number two. So, for example, in time slot 3, because player two's last move was A, now player one's current move will be A. So continue to choose C unless other player chooses B, then choose B or A. And after that, player one will choose A, onward. So we can find the summation and see that because playing A or AC like here, we can find this payoffs in each time slot and add them up together and see which one of them gets the highest payoff or wins the game eventually. But there's no eventuality like last move because it is an infinitely repeated game. Okay, let's consider another game. So let's say player one is playing strategy number 3, and player 2 is playing tit for tat strategy number 2. So they both choose C in the first time slot, and for the next time slot, for player 1, because it's playing the third strategy, player 1 will choose A because it has to choose A for even moves here. So the actions of player 1 are dependent of player 2. So player 1 goes CA, 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 CA. But now for player 2, we can see that actually here, so the second move is C because it says that then repeatedly play the last strategy played by the opponent. So this one is the last strategy played by the opponent. And for time slot number 3, this one is the last strategy played by the opponent. So that will be the current strategy for player number 2, and so on and so forth. And then we can get the summation and add them up and see which one gets the highest the payoff. Okay, so the last example is a Minimax Theorem example. So let's consider a cost function, negative 3x squared plus y squared minus 4xy. So we have strategy X, which maximizes the cost function, and a strategy Y, which minimizes the cost function. So this is the minimum strategy, and this one is the maximum strategy. Let's first solve for min max, in which we said that Y is the minimum strategy and X is the maximum strategy. So in both cases, X is under max and Y is under min. So we want to first find the result of min max of the function, cost function, and then compare it with the result of max min of this cost function. So for the first one, color blue. Uh, all right, let's consider this part, like the part that says max of this function with respect to x. So what we should do is to find the derivative of this function and equate it to 0. So the derivative of the function, the partial derivative of f with respect to x equals 0. That will be negative 6x minus 4y, which results in that x is negative 2 over 3y. And now we need to substitute this expression into f, because the next one is with respect to is a like optimization problem with respect to y. So we need all the variables here to be y, and there should be no x in this case in the cost function. So that will give us this expression, and we need to find the derivative of this expression now with respect to y, the second optimization problem, and equate it to 0, which will result in 10y. And from here, we can see that y is equal to 0. And because here y is equal to 0, x is also equal to 0. So the solution for this problem, for this first problem, is 0, 0 for both of them, x and y. Now we need to consider the second example. So the same procedure applies to this example as well, to this optimization problem as well. But here, because y is the first one, we need to derive, actually take the derivative of the function, the cost function, with respect to y first, and equate it to 0. So the partial derivative of f with respect to y, it gives us that y is equal to 2x. So because the last part is based on x, we need all the variables here to be x instead of y. So wherever we see y, we replace it with 2x. So it gives us this function. And what is the derivative of this function with respect to x? Actually, this says now that the maximum of this cost function with respect to x. So find the x that maximizes this cost function. So taking the derivative, there will be negative 14x equal to 0, x is 0, and from here we can see that y is 0. So the optimal solution for this problem is 0 and 0, which is also equal to this solution for this problem. So we can understand from here that min-max of this cost function is actually equal to max-min of this cost function. Therefore, we can say that min-max theorem for this example, for this cost function, actually holds. And so we don't get a different solution. So it's not always the case. You may sometimes get a different optimal solution for the other problem. But here we saw that minimax actually is equal to maximin. And I think, yes, that's it for this tutorial. And until next time.